Good day to all of you. Today we shall discuss on Armstrong's axioms or inference rules for functional dependency in DBMS. So functional dependencies are needed for normalization technique in any relational database design. With that, one can reduce the data redundancy in a database and eliminate updation anomalies, that is the problems related to insertion, deletion and modification operations. To define and simplify functional dependencies or to get one set of functional dependencies from another set, these Armstrong's axioms or inference rules are used. By the end of this session, you will come to know what are Armstrong's axioms or inference rules, how many inference rules are there, and what does each rule states. That will be clarified with example. So let's start the session. Armstrong's axioms, they are a set of inference rules which are used to infer, that is decide, all the functional dependencies on a relational database. Database means collection of related data. If data is stored in the form of tables, that is called as relational database. So another name for table is relation. So table has columns. These column names are called as attributes. So functional dependencies indicate the relationship between the different attributes or columns in a table. The functional dependencies are needed for optimized and efficient database design and normalization. So with normalization technique, one can reduce the redundancy in a database. Reducing redundancy means reducing multiple copies of data. Then ensuring data consistency means ensuring data correctness. So there actually function dependencies are needed. From inference rules, a new functional dependency can be derived using other functional dependencies. So these inference rules or Armstrong's axioms, they are used to define and simplify functional dependencies. That is first point. Next, if we have one set of functional dependencies, we can derive another set of functional dependencies from them. These rules were introduced by William W. Armstrong. Hence those inference rules, they are called as Armstrong's axioms. There are 6 inference rules. They are reflexive rule, augmentation rule, transitivity rule, union rule, decomposition rule, composition rule, and pseudo-transitivity rule. We shall know what are these rules one by one. Okay. Under core or primary inference rules, we have reflexivity, augmentation, and transitivity rule. Under derived or secondary inference rules, we have union, decomposition, composition, and pseudo-transitivity rule. Here A with arrow mark B indicates a functional dependency. That is the relationship between attributes A and B. The value of A attribute determines the value of B attribute. A is the determinant, B is the dependent. A determines value of B. So that is what is A arrowed B indicates. For example, in a student's table, the value of roll number determines the value of student name. Reflexivity rule states that if B is subset of A determines the value of B. Augmentation rule states that if A determines B, then addition of common attribute on both sides doesn't change the dependency. Transitivity rule states that if A determines B and B determines C, then A determines C. Union rule states that if A determines B and A determines C, then A determines both B and C. Decomposition rule states that if A determines both B and C, then A determines B and A determines C. Composition rule states that if X determines Y Z determines W, then XZ determines YW. Pseudo-transitivity rule states that if X determines Y, YZ determines W, then XZ determines W. Next we shall see Armstrong's axioms or inference rules as applied to a student table. First, let us see to reflexivity rule. Address of a student is set of street, city and state. So here street is subset of address and hence address determines street according to reflexivity rule, where if B is subset of A determines B. Here street is subset of address, hence address determines street. These are not shown in table here, but this example shows how reflexivity rule can give us a functional dependency, that is address determines street. Next we'll see to augmentation rule. In the student table, student ID is key, it can determine name. So student ID determines name, that is what is shown here. If we add common attribute department name on both sides, this functional dependency doesn't change, that still student ID is able to determine name of the student. That is what is augmentation rule states. If A decides B, then if you add common attribute C on both sides, still this functional dependency holds good, it doesn't change. This is how using augmentation rule we can obtain one more functional dependency from this functional dependency. Next we'll see to transitivity rule. Here in student table, student ID is the key. It can determine the value of any attribute in the table in any row. So student ID can determine name value. Similarly, it can determine department building value. But for this, first it determines department name for a student with ID 101. So CSE is the department name for student ID 101. Then once department name is determined, from that department building value is obtained. So student ID is able to determine department building value indirectly. That is what is transitivity rule states. So according to transitivity rule, if A determines B, B determines C, then A determines C. So student ID determines department name determines department building, hence student ID determines department building. So to apply transitivity rule, two functional dependencies are required. Here one functional dependency is student ID determines department name. Another functional dependency is department name determines department building. From these two functional dependencies, according to transitivity rule, we can write student ID determines department building. So from these two functional dependencies, this third functional dependency is obtained according to transitivity inference rule. Next we'll see to union rule. Union rule states that if A determines B and A determines C, then A determines both B and C. In this table, student ID is the key. Student ID determines student name, student ID determines student phone number, then student ID determines both student name and phone number. That is what is shown in union operation here. Student ID determines name, student ID determines phone. From these two FDs, now if we apply union rule, we can obtain one FD or functional dependency, that is student ID determines both name and phone. Here both the dependents are clubbed here. That is what is union operation. Next we'll see to decomposition rule. Decomposition rule is just the reverse of union. In union, both the dependents were clubbed. Here, what dependents are present in one FD, they are divided or decomposed here. Decomposition rule states that if A determines both B and C, then A determines B and A determines C. So student ID determines both name and phone. Then student ID determines name, student ID determines phone. So both the dependents what are present here, they are divided or decomposed here. That is what is decomposition, which is just the reverse of union operation. So in decomposition, instead of one FD, another two more simpler FDs are written. So this one functional dependency is expressed in terms of two other simpler functional dependencies. In union operation, two functional dependencies are expressed in terms of one functional dependency. In decomposition, one functional dependency is expressed in terms of two other simpler functional dependencies. Hence, we can say that decomposition rule is just the reverse of union rule. Next, we'll see to composition rule. Composition rule states that if x determines y and z determines w, then xz determines yw. So what you can observe here is, if this is fd1 and this is fd2, the x and z are determinants. They are put on one side in the fd3. If y is the dependent and w is the dependent, then yw dependents are put on the other side. So this is how FD3 is obtained. Now here in the student table, student ID determines department name value. State attribute value determines country attribute value. So if this is FD1, this is FD2. Student ID is X, department name is Y. State attribute is Z, then country attribute is W. Then XZ determines YW according to composition rule. So that is what is shown in composition rule as applied to student table here. Student ID determines department name. State determines country. Then student ID state determines department name and country. So using composition rule from two FDs, the third FD can be obtained. So from student table, student ID determines department name and state determines country. From these two FDs, one FD, that the third FD, that is student ID and state, determine department name and country. That is obtained. Next we'll see to the last one, that is pseudo transitivity rule. Pseudo transitivity rule states that if x determines y and yz determines w, then xz determines w. If you observe this rule here, this is fd1, x determines y. This is fd2, yz determines w. So fd3 is obtained. For that, in fd2, yz we have on determinant side, y is replaced by x because x determines y. So when x determines y, y is replaced by x. Hence, determines w is written as xz determines w. So as applied to student table here, student ID determines name. Then student name and department name both together determine department building. Now since student ID determines name, name is replaced by student ID. So the third FD we have student ID and department name determine department building. This is how, using pseudo transitivity rule, the two FDs are expressed in terms of one, that is third FD. That completes the discussion on applying all these 7 inference rules as applied to student table. So those examples are shown here. Next we shall move on to study what are the advantages and disadvantages of Armstrong's axioms or inference rules for functional dependency in DBMS. Advantages of using Armstrong's axioms for functional dependency in DBMS are: for a given set of functional dependencies, systematically and efficiently, another set of functional dependencies can be obtained. It helps to optimize database design. These inference rules can be used to identify redundant functional dependencies, means repeated functional dependencies. This helps to eliminate unnecessary data and improve database performance. These inference rules can be used to verify whether a set of functional dependencies is a minimal cover, which is a set of dependencies that cannot be further reduced without losing information. So these are the advantages of Armstrong's axioms or inference rules for functional dependency in DBMS. Disadvantages of Armstrong's axioms for functional dependencies in DBMS are: the process of using Armstrong's axioms to find additional functional dependencies is computationally expensive, especially in case of large databases with many tables and relationships. The axioms do not take into account semantic meaning of the data, and they may not always accurately reflect the relationships between the data elements. The axioms might give large number of functional dependencies, which can be difficult to manage and maintain over time. So these are some of the disadvantages of Armstrong's axioms for functional dependencies in DBMS. That completes the whole discussion on Armstrong's axioms. How many rules are there? What does each rule states? How they can be applied to find the relationships between attributes or functional dependencies in a table, and how they can be used to derive one set of functional dependencies from another set of functional dependencies. Then what are the advantages and disadvantages? Stay tuned. In next coming video sessions, I will be discussing on the extending topics of these, that is finding the attribute closure, first one, finding minimal cover, then how to find candidate keys using these inference rules and functional dependencies. Then we'll be able to solve some of the important problems in DBMS based on functional dependencies and keys in DBMS. I hope you understood. Thank you.